Good morning, everyone. In previous lecture, we learned how to evaluate normal stress, shear stress, or tangential stress on any oblique plane in different cases. So, first case we observed that when there is a bar and only one normal stress is acting in one direction. So, this was the case number 1 we learned. After that, we learn how to evaluate again normal stress and tangential stress acting on a bar when there are two mutually like principal stresses, that is sigma x and sigma y, acting on the bar. So in that, how to evaluate the normal stress, then tangential stress, resultant stress, angle of obliquity, that is angle between the normal stress and the resultant stress. So this we already evaluated, and from that we already learned how to evaluate the maximum shear stress also, principal plane where shear stress is 0, that we learn. So after that we also learn how to evaluate the normal stresses and maximum shear stresses when there is a simple shear stress is acting. So I will ref. So third case was when bar is subjected to a simple shear stress. So again this will have a complementary shear stress. What is principle of complementary shear stress? So this was the our case number third. After that we combine both these cases, so case number 2 and case number 3. So here I will show you when members are subjected to two like mutually perpendicular direct stresses. So these are the two mutually perpendicular direct stresses, that is sigma x, so sigma y, accompanied by a simple shear stress. So here I am showing the shear stress. So by combining these two cases, we learn the case number 4. So all derivation I have mentioned in detail in my previous videos. If you have not seen, please go to the playlist and watch that video. So in last lecture also I covered numericals on all these three cases. Today I will summarize or cover some important three numericals based on the case study 4, that is when two mutually perpendicular stresses, alike stresses, acting on a body along with the simple shear stress. So in that, first we will see the first numerical. So let's start the numerical reading. A rectangular bar block of material is subjected to tensile force. So one tensile force is given, that is 110 Newton per mm square on one plane, and a tensile stress of 47 Newton per mm square on a plane right angle, means two mutually perpendicular stresses are given and both are like means both are in tensile nature. If one force is tensile and another force is compressive, then it is called as a unlike forces. So both are tensile, so like forces are there. Each of above stresses accomplished by a shear stress. So again, what is given? So tensile stress sigma x is given and sigma y. Why I am writing sigma x and sigma y? Because they are at right angles. So I am considering sigma x, that is, so here I will write given data. I will consider first shear stress along x direction, so 110 Newton per mm square. Then sigma y, it is given 47 Newton per mm square. and it is accompanied by a shear stress, that is tau, sigma 3 Newton per mm square, that associated with a formal stress tends to rotate the block in anti-clockwise direction. So the direction must be anti-clockwise. So in that, what is required? What they have asked? They have asked to find the direction of magnitude of each principal stress, and second is we need to evaluate the maximum shear stress. So first I will draw the diagram. From this information you might have observed that this is a problem based on case number 4, as here two forces are acting. Clear? So what are the two forces are there? So along x direction it is sigma x, and along y direction it is sigma y, along with the shear stresses. So this is shear stress tau, again this is shear stress tau, and shear stress tau. Let's say this is A, B, C, D. Now here we need to find out the maximum magnitude and direction of principal stress. So here the plane we need to evaluate where the shear stress is 0. So we did the derivation, and from that we came to know, or we evaluate the formula to calculate maximum principal stress and minimum principal stress, is also known as major principal stress and minor principal stress. So from the given data I will write formula for first major principal stress. So that will be equal to sigma n1, that is equal to sigma x plus sigma y divided by 2 plus under root of sigma x minus sigma y divided by 2 whole square plus tau square. So how this formula come? Go to the previous video, you will get the idea how the major principal stress formula came out. So if you just put all the information in this formula, then we will get the major principal stress. So 110 plus 47 divided by 2 plus under root of 110 minus 47 divided by 2 whole square plus tau, it is 63, it is given 63 square. So if you calculate, then it comes near about 110 plus 47 divided by 2, it is 78.5 plus under root of 110 minus 47 divided by 2, that is 31.5 plus 63 square. So this value, it is near about 148.936 Newton per mm square. So all the details are given in Newton per mm square, so no need to convert any unit. So this is the value for major principal stress, 148.93 Newton per mm square. So next is we need to evaluate the minor principal stress. So I will write minor principal stress. So what is the difference between these two? It is just the negative value. So here if you consider negative, then you will get the minor principal stress. So sigma n1, that will be equal to, here I am just considering the minus, so I will write formula, that is sigma x plus sigma y divided by 2 minus under root of sigma x minus sigma y divided by 2 whole square plus tau square. Why I have evaluated this one? Because I am just mine I am doing just a difference between these two values. So here I will get direct value, it is near about 8.064 Newton per mm square. So this is the sigma n2, that is minor principal stress, and it is near about 8.064 Newton per mm square. Simple. So this is all about the magnitude of principal stress. Now what is asked? Direction also asked. So when we derivating the problem, so at that time we came to across that another formula, that is direction. For direction, tan of 2 theta equal to 2 pi, sorry, 2 tau sigma x minus sigma y. So here 2 into 63 divided by 110 minus 47, so it will be here about 2 into 63 divided by 110 minus 47, it is near about 2, then 2 theta 2 theta equal to tan inverse of 2. So tan inverse of answer, it is 63.47, and when we evaluate for theta, so it will be divided by 2, so it is near about 31.71 degree. Clear? So this is the location of major principal stress. Now we know both major and minor principal stress are at 90 degree. So if you add 90 degree, then I will get theta 2, or angle of minor principal stress, that is 121.71 degree. So remember, we need to evaluate the position of both the major and minor principal stress. So what is next? Next is magnitude of maximum shear stress. So we have a formula, that is number 4th, maximum shear stress, that is sigma T max. It is half of sigma x minus sigma y whole square plus 4 tau square, or you can use this one also. So this is the also a maximum shear stress formula, just I am taking 1 by 2 outside the this under root. So if you put the value of sigma x, that is 110, minus sigma y is 47 square plus 463 square, then it is near about 70.436 Newton per mm square. So these are the answers for this problem. I hope you understand this simple formula, in which there are two mutually like forces are acting on this body along with a simple shear stress. Now let's go to the next problem. Now here if you observe, a point in a strained material is subjected to a stresses as shown in figure. Now here they are asking about the location of principal plane and principal stresses. Now here if you observe from this figure, if when you observe, then you may thinking that there are two forces are acting over here and both are normal. That is wrong. Normal means it must be perpendicular. It is not perpendicular, so it is at 60 degree. Clear? So due to this force, there will be two forces will be act on this particular plane. So let's say A, B, C and D. So when such problems come into the exam, then we need to resolve these particular forces in two direction along this AD. If you observe this particular plane AD, then I can resolve this particular plane into two direction. So how I can resolve? Just see. So here I can say that along this plane I will get 60 cos of 60. So that will be a, a tangential force, or sorry, yes, that is will be a tangential force, or that will be a shear stress. So value 60 into cos of 60, so it is 30. Next, when I resolve this force along x direction, then I can resolve force in this direction, that is normal stress along x direction. So that will be 60 into sine of 60. So sigma x will be 60 into sine of 60. So the value of this particular force will be a 50.96, 50.96 Newton per mm square. So these are the values. So first I will get sine 60 into multiply by 60. Okay, so how to evaluate this? First you evaluate sine 60 and multiply by 60. So here you will get the sigma x is equal to 50 Newton per mm square. So similarly, when you resolve these forces, then definitely you will get the same value. So along this direction that will be the tau, and along this direction that will be the sigma x. Now as we know the principle of shear stress, complementary shear stress, from that I can draw another figure. Here I am drawing the same figure. Then I will get to know that there are different forces are acting on this particular body. So along x direction it is 50.9 Newton per mm square. Along y direction it is already given, that is 40 Newton per mm square. Again 40 Newton per mm square. So along x direction that will be 50.90 Newton per mm square. So here if you observe, there is a shear stress is acting in this direction, that is 30 Newton per mm square. In upward direction again tau will be 30 Newton per mm square. So on this particular plane, if you observe A, B, C and D, on this CD also there will be a shear stress will be acting, and that value will be definitely equal to shear stress which is acting on this plane BC, 30 Newton per mm square. Likewise on this plane AB also there will be shear stress of value 30 Newton per mm square. So why this I am writing? Because this is because of the principle of complementary shear stress. So this problem we have converted in this problem. So here if you observe, there is a sigma x, it is near about 50.90, sorry, uh, let me check the value. Sine 60 into 60, it is 51. So there is a correction, it is 51.96 Newton per mm square. So everywhere this is 51.96, 51.96, 51.96. Clear? So there was some calculation mistake. Then sigma y, it is already given, that is 40 Newton per mm square, and tau we have evaluated, that is equal to 30 Newton per mm square. Clear? Now what is asking? Principal stresses. So and location. First we will see the location, that is similar, same formula which you have used in previous case, that is tan of 2 theta, tan of 2 theta equal to 2 tau divided by sigma x minus sigma y. So that will be equal to 2 into 30 divided by 51.96 minus 40. So 2 theta, that will be equal to 2 into 30 divided by 51.96 minus 40, it is 5.01. So theta will be equal to divided by 2, so 2.50. So if you convert in degree, so theta will be equal to 2 degree 30 minutes. So on calci you need to press this, then you will get the value in degree and minute. So this is then 2 degree minute. Next theta, it is one major principal stress, and what about minor? We need to add 90, so it is near about 92. Wait, so there is some mistake again in calculation. This is tan 2 theta. Clear? So this is tan 2 theta. We must consider tan inverse of 5.01. So it is near about 72.71 divided by 2. Then here I will get theta equal to 39 degree 21 minute, and another theta 2, that will be plus 90. So here I will get 129 degree 21 minute. Clear? So this is our first answer. Next, evaluate the principal stresses. So it is similar, same formula which we have used earlier, that is sigma major principal stress, that is equal to sigma 1 plus sigma 2 divided by 2 plus under root of sigma means sigma x minus sigma y divided by 2 whole square tau square. If you just put the values of sigma x, it is 51.96 plus 40 divided by 2 plus under root of 51.96 minus 40 divided by 2 whole square plus tau. Tau value is 30. So if you evaluate, then it will become 45.98 plus 30.6. So it is 76.58 Newton per mm square. So this is sigma major. How to evaluate minor? Minor principal stress, just instead of plus value here take negative. So if you just take negative, sorry, minus 45.98 minus 30.6, if you take the difference, then here you will get directly 15.38 Newton per mm square. In exam you need to write the formula and then you will get direct answer over here, because here I am evaluating these two factor. Just if you take a negative or difference between these two value, then I will get the minor principal stress value, and this is value for the major principal stress, and the position is at theta 1 major, and here you can locate the minor at 90 degree. I hope you understand this second problem also. Now another next problem. All three problems are not similar. Something is different in all problem. So here let's understand what is difference in this case. At a certain point in a metallic bar under stress, the intensity of resultant stress on vertical plane is 1000 Newton per mm square. So here 1000 is given. It's mistake. 1000 Newton per mm square is given, which is inclined at 30 degree to the normal to the plane and stresses on a horizontal plane, has a normal tensile component of 600 Newton per mm square as shown in figure. Find the magnitude and direction of resultant stress on horizontal plane. Now here if you observe, two planes are given. This is CB is horizontal and AB is vertical plane. So what they are asking? They are asking about the magnitude and direction of resultant stress on horizontal plane, not on entire body. So let me clear all of you. When we evaluated the formulas, it is for the oblique plane, clear, and after that we evaluate the principal stress where shear stress is 0. From that we got some formulas. However, in this problem statement they are asking specific on only horizontal plane. So here horizontal plane is BC. Now here we need to take care about only the forces acting on CB, clear. So this is 1000 Newton per mm square force. We need to resolve in two direction, that is 1000 into cos of 30, and here I can consider 1000 sine of 30, clear. So here if you observe the normal component, it is 1000 into cos of 30. So this value cos 30 into 1000, it is 866 Newton per mm square, clear. Now sine 30 into 1000, so it is 500 Newton per mm square, clear. Now first we will see the resultant stress acting on this particular BC, clear. Resultant stress acting on this particular shear stress BC. So if you observe, we already learned. Now I will consider the plane CB only, clear, and here I will separate the plane AB. On this plane, if you observe, the normal force, that is 866 Newton per mm square is acting, and here if you observe, shear stress tau is acting, it is having 500 Newton per mm square. Now, as a principle of complementary shear stress, on this BC plane there will be a tangential or shear stress acting on this particular plane, that is near about, that is 500 Newton per mm square. Next, there is another force, that is normal force acting on this particular body, that is sigma y. It is given 600 Newton per mm square. What they are asking? They are asking about this resultant stress acting on this particular body. Clear? So when you shift this particular sigma y over here, then I will get triangle like this. So this is sigma r, here I am taking tau, and this will be the sigma n or sigma y. So this value is 600, tau value is 500, and we need to evaluate the sigma r. So from this I can directly write resultant stress on horizontal plane, that is under root of sigma y or sigma n square plus tau square. So it is under root of 600 square plus 500 square. So 600 square plus 500 square under root of this, then I will get 781.02 Newton per mm square. So this is the resultant stress value. Clear? Now if you observe this particular figure, then if I consider the normal stress, that is along sigma y and tau, so here I can write tan theta equal to sigma 2 divided by tau, then it is 600 divided by 500. So here 600 divided by 500, tan inverse answer, it is 50 degree 11 minute. So this is the position of resultant stress on horizontal plane only. Clear? Now, so first is complete, that is find the magnitude or direction of resultant stress on horizontal plane, and then they are asking about the principal stresses. So for principal stresses, we have sigma x, sigma y and tau. So sigma x is 866 Newton per mm square, sigma y is 600 Newton per mm square, and tau is 500 Newton per mm square. So we will use same formulae as this is the fourth case, that is two mutually perpendicular stresses acting on a body accomplished by the simple shear stress. So major principal stress sigma n1, that will be equal to sigma x plus sigma y divided by 2 plus under root of sigma x minus sigma y divided by 2 whole square plus tau square. So from that equation I will put the all values, that 866 plus 600 divided by 2 plus under root of 866 minus 600 divided by 2 whole square plus sorry 500 square. So from this I can will get the value of sigma n1, that is major principal stress, equal to 733 plus 517.38. So why I am writing these two? Because I need to evaluate minor principal stress also. So major principal stress, that will be equal to 1250.38 Newton per mm square. So this will be the major principal stress. Now here I will evaluate minor principal stress, that is sigma n2. So that will be just a negative over here, then entire formula that will remain same, that is sigma x minus sigma y divided by 2 whole square plus tau square. So if you take negative or difference between these two value, then I will get sigma n2 or minor principal stress, that is 215.62 Newton per mm square. I hope you understand the concept of principal stress and its location. So we have taken three different cases. Here there was a simple case, two forces acting mutual perpendicular along with shear stress. So here we have resolved the forces in normal direction and in tangential direction. Then we evaluate the principal stress and stress, and in third problem we evaluate principal stress on a single plane, sorry, resultant stress on a single plane, and then we evaluate the major and minor principal stress. I hope you understand the numericals based on this principal stress and strain. In next lecture we are going to see the Mohr's circle. So this was the analytical method. Next we will see the graphical method to evaluate the principal stress and principal strain plane and its location and direction. Thank you.